Hello guys, welcome to another tutorial session of the Applied Electricity course. Okay, we are going to talk about the Applied Electricity once again. And this time, we are going to talk about the Thevenin's theorem and the Norton's theorem. Please, if you've not watched the fundamental video and other videos, try as much as possible to watch them. Okay, I'll put all the links in the description. And we've really moved far. So if you watch those videos, people are giving testimony that when they watch it, they get the concept very well. So please try as much as possible to watch them. Okay. And I believe that you not see applied electricity as a difficult course. And I can assure you that if you follow me very well and understand everything that I do here, you are likely to get 80% in your course. So try as much as possible to do what? To watch them. Okay. So let's move on. We are going to talk about the Thevenin's theorem and the Norton's theorem, as I said. So let's start with the Thevenin's theorem. Okay. So let's analyze the statements. The statement says that in Thevenin's theorem, right, it is possible to simplify any linear circuit, irrespective of how complex it is. No matter how complex the circuit is, right, I can simplify it to just an equivalent circuit with what? With a single voltage source and a series resistance. And this single voltage source is termed as VIII. And the series resistance is termed as RTH. The subscript representing Thevenin. So Thevenin voltage and Thevenin resistance. So let's see. Assuming I have, let's say, a complex circuit like this. Let me take something like this. And the voltage source. Okay. So let me draw a very complex circuit because I'm not going to solve anything over here. So let's try as much as possible to solve a complex circuit here. You get it? Yes. So I have a complicated circuit. We will solve an example, but I want to explain things to you. Okay, so this is a complex circuit, and I want to find, let's say, the current at this point. Let's say the current flowing through this load, right? So I have R1, R2, and R3. And I have IA and let's say VA. So what is Thevenin saying? Thevenin is making a statement that this is a very complex circuit, right? This is a very complex circuit. All this one. I want to find the current flowing through the RL. So in that case, I can reduce this complex circuit here, right, to just a voltage source in series with what? A resistance. So we have the VIII here, the RTH here. Then with this result, we can connect it to what? To where we are finding the load, the resistance in which we are finding the load. That is the RL. So a complex circuit which has the resistance, a complex circuit which has about, let's say, 3 resistance and a current source together with a voltage source, I've been able to reduce it to what? To a voltage source, right, and a resistance, which are in series, and they are connected in series with the load. So that is the target. That is the vision. The vision is to reduce all this complex circuit to just a simple voltage and resistance. Okay. And the voltage is called the Thevenin voltage, and the resistance is called the Thevenin resistance. So with this one, it's very simple to solve. We are going to talk about it very soon. In our next video, we are going to solve an example. Okay. So that is it. Our target is to make sure that all this complex circuit has been reduced to what? A voltage source and a resistance in order to what? To find the current flowing through the resistance. which with this is very simple. So in that case, I'm going to give you a basic formula for the VTH and the RTH. So when you get a circuit like this, then what's going to be the VTH? You can apply for the, let's say, the voltage division if you want to find the voltage in the RL. But if you want to find the current here, which is the same as what the IT, then we can say that from Ohm's law, VTH should be equal to what? RTH plus RL, right? RTH plus RL on IT. So in that case, if I want to find the IT, or let me call this IRL, that is the current that is flowing through the load. Okay, so with this, if I want to find IRL, I just need to what? Say is VTH all on what? On RTH plus RL. So that's the basic formula. That is, if I want to find the load, that is the current that is flowing through what? The load. With the voltage drop, right, I'll just use the voltage division. Do you get it? That is the vein that is flowing through the load. It's simply going to be what? It's going to be the RL all over what? RTH plus RL times what? Times VTH. But basically, most of the time, they will ask you to find the current. Most times, they don't ask you to find the load. Okay. They don't ask you to find the voltage across that drop. But most of the time, they will ask you to find the current that is flowing through the load. So with this, we can move on. If you don't understand anything, please reverse the video to get the concepts. Okay. So let's solve a question. This is a typical question. And the question is saying that using what? Thevenin's theorem, we should find the equivalent circuit to what? To the left of the terminals in the circuit below. So this is the terminal. This is the left of the terminal. So he says you should find an equivalent circuit to the left of the terminal. Then we should find the current I. That is the current that is flowing through what? The 1 ohm resistor. Okay. So let me just label this as R1, R2, R3, and we have the RL for better understanding. Okay. So our target is to make sure that we reduce this complex circuits. Right. This complex circuits. Our target is to reduce it to what? To just a VTH. Right, sorry. To a VTH, right, and an RL in series. So that we'll be able to what? Connect it to the 1 ohm resistor. We'll be able to connect it in series with what? With the 1 ohm resistor. So that's our target. So let's pick that circuit out from the question. So we have that complex circuit here. I have my plus minus, and this is the 12 volts, right? Then I have my 6 ohms here, which is same as R1. Then I have a current source, right, which is 2 amps. Then I have my 6 ohm, right, and a 4 ohm resistance. Okay. Then I have my terminals here. That is the A and B. A and B. So I've taken it out. Do you get it? So with this circuit, my target is to find the RTH and the VTH. So how do you find RTH? Let's start with RTH. Right. We are finding the RTH. With RTH, right, we take off all the active sources. So with RTH, right, we take off all the active sources. It's a very key information. That's the reason I'm writing it. So we take off all the active sources, right, in the circuits. And we already know that, in the circuits, right. So we already know that if we have voltage source, that's from our previous video when we are doing the superposition. We take it off by doing what? By writing what? Short circuits. By short circuiting it. So we take it off by short circuiting that path. And if it's a current source, we take it off by what? Opening circuiting that path. So that place becomes open circuits. So open circuit here. And here is short circuits. Please, if you've not watched the superposition video, do well to watch it. Okay, so that you get the concept over here. So when it's a voltage source, we short circuit the path. But if it's a current source, we open circuit the path. So that is the ideology we are going to use in finding the RTH. So we always find the RTH at the terminal of what? Of the circuit. So let's draw the circuit for RTH. So RTH circuit will be something like this. So at this point, I short circuit the path. So this one will be short circuited. So we short circuit the path. Then let's move on. So we have the 6 ohm resistor here, which is R1. Right. Then we have a current source, which is going to make it an open circuit. Okay. Then we have the 6 ohm resistor here. Then we have our 4 ohm resistor here. Okay. So then we have our terminals here where we are supposed to find the RTH. So finding the equivalent resistance of the circuit here will give us the RTH. Okay. So here is very simple. This is one of the simplest circuits you can ever get. You can see that we have the R2 and the R3. I'm losing my labeling. So we have the R2 here and we have the R3 here. You get it? So with this, the 6 ohm and the 6 ohm resistance, they are in series. So R1, R2 are in series. So if I should reduce it, I'm going to get something like this. A resistance here, which is 6 plus 6 equals to what? 12. Right? 12 ohms. Then I'll get my 4 ohms here. 4 ohm resistance here. Okay. Then I still want to find my RTH. So now at this point, I can see that these two resistance, that is the R12, the combination of the two resistance in series, and the R3, they are in parallel connection. So how do you find the RTH? RTH is equal to what? The R12 multiplied by what? R3, all on what? R12 plus R3. And with this, what do I get? I'm going to get 12 times 4, all on what? 12 plus 4. And this will give us 48 on what? On 16. So what's going to be 48 on 16? So 48 on 16 is going to be basically 16 can go into this itself, right? And to get into this 3 times. So we have 3 ohms. Right? So the RTH we found, and this is going to give us 3 ohms. Very good. So now our target is to find the VTH. So this time, we bring back all the sources that we took from the circuit, we bring them back. So let's draw the circuit again. We're having a voltage source here. That was plus minus, and it was 12 volts, right? We'll visit the question again. So we are drawing this circuit. And we had a 6 ohm resistance here. 6 ohm resistance here. Right. Then we had a current source down here, which was moving upward. So let's see. So the current source was moving upward, which was 2 amps. Okay. So we have our 2 amps here. Then we have our 6 ohm resistance again, connected towards a 4 ohm resistance. Then we have the terminals there. So this circuit is used to find VTH. As soon as I'm able to get the voltage across this terminal, then I'll get my VTH. So what is the vision? The main goal is to find the current through what? The 4 ohm resistance. So I 4 ohms. So once you're able to find the current through the 4 ohm resistance, then it will be what? The same as VTH. That is, after finding the current, if I'm able to find the voltage through, once I get the current, it's easy to what? To get the voltage. That is VIII 4 ohms. So once I get the VIII 4 ohms, it is the same as what? VTH. So the target is to find the VIII 4 ohms. So after getting it, I'll just make it the VTH. So with this, what can we do? Yes, there are a lot of ways you can use in solving. You can use, how do you call it? The mesh, that's the super mesh hierarchy. You can also use the current division, voltage division, source transformation, a lot. So at this time, your thoughts or your mentality should click very well. Hierarchy. So that you will not spend a lot of time finding the current that is flowing through the 4 ohm resistor. After looking at this circuit, I discovered that once I'm able to find the current that is flowing through the 4 ohm resistor, I'll quickly get the VIII 4 ohms. That's the voltage through the 4 ohm resistor. Then I just equate it to VTH. Because with this one, I can say that VIII 4 ohm is equal to what? The VTH. Do you get it? So that's the target. So what can we do here? What can we do? We can basically redraw the circuit. I can apply, how do you call it? Source transformation to find the total current, right, for this. So let's see. Let me apply source transformation over here. This resistance is what? In series with the voltage here. You get it? So the new equivalent circuit is going to be something like this. I have a current that is moving upward. Please, if you've not watched the source transformation video, try to watch it. Else you'll be confused over here. I've made a video on source transformation. That's the reason why I'm not going into details when it comes to analyzing this circuit. So with this one, what will be the current value? You already know that it's going to be what? 12 on 6. That's the voltage over the resistance. Right. So at the end, we are going to get 2 amps here. Then it will be in parallel connection with what? With the 6 ohm. Right. 6 ohm resistance. We will also have our current source here. This current source, we've not done anything to it, so we have the 2 amps here. Then we have our 6 ohm and the 4 ohms. Right. Okay. So with this, now I can find the total current for this simple circuit. Let me put my VTH here so that you not be confused. Okay. But anyway, I can take it up as I'm analyzing. Then later on, I'll just bring it there. Okay. So the reason why I can take it off is because you see this is an open circuit and current is not flowing through that path. So the current through that path is 0. The current here is equal to 0 because this is an open circuit. Okay. So I can take it off. Since it's an open circuit, I can take it off. Do you get it? So with this, I can find another equivalent circuit. I can combine this current to this current because there is no resistance between them. So I can combine the two of them. Okay. So I can get a simple circuit like this. Sorry. A current source which is moving upward. Then 2 plus 2 will be what? Will be 4 amps. So I'll get my 4 amps here. Then I'll get a resistance. That is 6 ohm. Right. That's 6 ohm resistance. And I have my 6 ohm plus. Let me add this. These two are in series. You get it? The current that is flowing through this 6 ohm is the same as the current flowing here. They are in series. Why? Because I made it clear that on this path we have an open circuit. So I is 0. So all the current that is flowing through this one comes to pass in the 4 ohms. Okay. So I can make this one 10 ohm resistance. So after finding the current here, this is the same as the what? As the I4 ohms. Do you get it? So this is the same as the I4. So after finding the current through the 10 ohm resistance, it will be the same as the I4. Because if the current is flowing, right? If the current is flowing, this path, right? It's flowing through this path. Let me erase it, sorry. So the current is flowing through this path. It's the same. No current flows here. The I is equal to 0, which I stated here clearly. So no current is flowing through there. Because it's an open circuit. It's an open circuit. I've repeated myself over and over again because this is where students used to find the confusion. Are you okay? So please take note of it and it's going to help you. So at the end, what's going to be the I4 ohms? Basically, they are going to apply the current division. Are you okay? So with the current division, what do we get? We are going to get 6 on what? On 6 plus 10. Right. Times 4. So that's it. So it's going to be 6 on 16 times 4. Do you get it? So what do we get here? 4 goes into itself. 4 goes here 1. 4 goes here 4. So the I4 ohms is basically 6 on what? On 4. And this is going to be 2 goes into itself. 2 goes here 2. 2 goes here 3. So I4 ohms is simply going to be what? 1.5. 5 amps. Okay. So we have 1.5 amps as the current that is flowing through the 4 ohms resistance. Do you get it? Okay. So now that we found the current that is flowing through the 4 ohm resistance, then we can find what our V4 ohms, which is the same as the VTH. And how do you find it? You are just going to multiply the current. That is 1.5 times, let me write the formula first before someone gets confused. So we can say that it is 1 4 ohms multiplied by what? The current, that is the resistance over there. You get it? So at the end, what do we get? You are going to get 1.5 times 4. And that gives, so 1.5 times 4 will be 6. So the VTH is 6 volts. Are you okay? So it's very easy to find the VTH over there. So now we've been able to find the RTH. What was the RTH? The RTH was, we found the RTH as 3 amps. Are you okay? So now that we found RTH to be 3 amps, then and the VTH to be 6, right? We can draw an equivalent circuit. That is, our VTH is 6 volts, right? And the resistance was 3 ohms. So now we can connect it in series with what? The 1 ohm resistance, where we were asked to find the, how do you call it? We were asked to find the current, that's the I. We can connect it in series with our 1 ohm resistance. So let's go back. So we are connecting it to our 1 ohm resistance here. Okay. And with this, it's very easy to solve. The formula is always the same. And I've already proven the formula, right? I've proved the formula. And this was it. If you want to find the current, it's basically what? The voltage divided by what? The sum of the resistance. So, in that case, if you want to find the current that was labeled as I, the current was labeled as I. So, I is simply going to be what? It's simply going to be the voltage source, which is 6, all divided by the sum of the resistance. That is 3 plus 1. Okay. And this gives what? 6 on 4. And that is equal to, how do you call it? It's equal to the 1.5 amps. You get it? So that is the concept of Thevenin. So the 6 volts, the 3 ohm, and the 1 amp. So we're able to find the current that is flowing through this resistance. That's the 1 ohm resistance. And that gives 1.5 amps. Are you okay? Yes. So that's the Thevenin. We have a lot of questions under it. Probably within the week, I'll solve more questions under the Thevenin's theory. But for now, this is the concept of Thevenin. I just want you to watch the video and understand it, so that if I solve my next question under Thevenin, I'm going to look for one complicated circuit and apply both Thevenin and Norton. So with this, I'm going to get 2 series of videos, right? I'm going to get this one. I've already explained to you. Watch this one very well so that you understand. So once you understand it, then the next one becomes easy. Solving it, I'm not going to explain it as I'm doing over here. Are you okay? So please try as much as possible to understand the concept. If you don't understand, please reverse the video and get the concept very well. So let's move on to the Norton. Are you okay? With the Norton, it says that, right, any linear circuit can be simplified to what? To an equivalent circuit consisting of what? A single current source and a power resistance that is connected to the load. So basically, what it's trying to say that, assuming I have my complex circuit over here, that same complex circuit, let me assume that I have a complex circuit over here, and I have a current source too, right? I'm just drawing something to represent a complex circuit. And I'm asked to find the current that is flowing through what? The RL load. So I have R1, R2, R3. Then I have, let's say, VA and VB, IA, right? Nothing is trying to say that. If let's say I have this circuit, I can reduce all this one to what? To a current source in parallel with what? A resistance. that is Rn. Then we have the In. I can reduce the circuit towards a current source in parallel with what? A resistance. This time not in series. Current is always parallel to resistance. So I can reduce it in parallel to what? A resistance. Then I connect the load to it. I connect the load to it. That is the RL. Are you okay? So if I want to find the current that is flowing through with this, if I want to find the current that's flowing through the load, we are going to apply what? The current division. So it's basically going to be what? The Rn all divided by what? Rn plus RL multiplied by what? Multiplied by the In. Do you get it? Yes. So that's it. And if I want to find the voltage across the load, that is, I always need to find the current, and I'll multiply it with what? The current, to get the voltage across the load. Are you okay? So that is Thevenin's theory. Instead of making it in series, a voltage source in series with a resistance, with Thevenin it says that we just need to convert it to rather a current source. Then it will be in parallel with what? The Rn. Okay, so basically the procedure for finding Rn is the same as the procedure for finding RTH. Okay, so Rn and RTH, they are always the same. It's just that the In is not equal to what? The VTH. So the procedure for finding the In is different from the procedure for finding the VTH. But at the long run, they all have the same concept when you are finding what? The Rn. Okay. So that is it. The two are related. If let's say you get objective question, you don't need to, and you are asked to find, let's say, In, and you are struggling to use the In procedure, you can just apply the Ohm's law. We state that the VTH is related to the In based on what? Ohm's law. So VTH equal to In multiplied by what? The RTH or Rn, any of them, because I said that the Rn and the RTH, they are the same. So this is the relationship between the Norton current and Thevenin voltage. So if you are struggling in objectives, if you are struggling to find the VTH, but you can find the In, use In, then you come and use this relation. Are you okay? So let's solve a question under the Norton theorem. Are you okay? So we are going to solve a question under the Norton theorem. So with this question, let's analyze the question. The question is stating that we should find the Norton equivalent circuit to what? To terminals A and B, right? So we should find Norton equivalent circuit to terminal A and B. So these are terminals A and B. So we are finding the equivalent circuit for all these ones. Let me draw a short dashes around it. So we are finding the equivalent circuit for this terminal. So this complicated circuit here, the question says we should find an equivalent circuit for it. So he's trying to tell us that we should find one current source and a voltage source in parallel. Something like this. So I have one current source here and a voltage source, right, in parallel. Then I can connect the other two which was taken out from it. So I've taken this 180 amps from it. And I also took the RL from it. So something like this. You get it? So in that case, I'll have the In, which you'll find over here. Then we have our Rn, right? Then this I, let me call this one I2, right? And this I1. So this I2 here, then we also have our RL. So this is what the question is saying, that at the terminal we should find the equivalent circuit. So it's very simple. If we are finding the equivalent circuit, we need to bring out that complicated circuit. So let's bring it out. Now next diagram, let's bring that one out. So bringing it out will be, let me draw it here. Okay. So bringing it out will be something like this. So I have my voltage source. Okay. Then I have my resistance. That's nice. Then I also have my current source downwards. Okay, fantastic. So you see, assuming we are supposed to produce current here, the current should be moving what? Downwards, right? So the Norton current will move downwards. So if we should produce current, it will be moving downwards. So the Norton current is always going to move downwards. Are you okay? So here we have the 120 ohms here. We have R1. Then the E is considered as 24 volts. Then we have the 280 ohms here, which is the R2, right? And we have, let me convert this to, how do you call it? Amps. So I'll just move 3 times. So I have 560 times 10 to the negative 3, right? And this is the same as 0.56. So I have 0.56 here, right? That's it. So we have our terminals A and B. So what do you do? Let's first find our Rn. This time I'm going to divide the board into 2, where I'm going to find Rn at this side, Rn at this side. Now find the In at the other side. Okay, so with the Rn, this is the circuit for the In. I remove all the, how do you call it? I remove all the active sources. Okay, and if I see a voltage source, I change it with what? A short circuit. Right? And with the current source, I always change it with an open circuit. Okay, so let's remove all the active sources. So removing all the active sources, it becomes something like this. So I'll short circuit that part. With a short circuit, right? Then we move on. I have a resistor which is power to, you get it. Then I have a current source which will be an open circuit. You get it. Then I have my Rn at this side. So finding Rn is the same as RTH. Okay. There's no difference. Rn and RTH, they are the same. So the technique in finding RTH is the same as the technique used in finding what? The Rn. So I have my Rn at the side, right? This is 120 ohms. That is R1. And I have 280 ohms, which is R2. So you can see that these two, they are in parallel connection. So Rn is basically going to be 120 times 280, all on what? On 120 plus 280. Do you get it? Yes. And what would that be? So that would be what? 84. So we are going to get 84 ohms. Okay. So that is for Rn. So what about In? We return the active sources. So all the active sources which were taken out from the circuit, we return them. So let's return them. So we are going to use the same circuit up there, right, to find our IN. Sorry. So we have the similar circuit there. Then we have our current source, right, which is moving down. So at this point, it's very simple, right? We are going to short circuit that path. If you are finding Norton current, we short circuit the path. But with VTH, we open circuit it. So at this time, it's going to be a short circuit over here, right? And that gives our IN. So the current that is flowing through this side is called the IN. Okay. So we have 0.56 amps here. And we have 280 ohms at this end, that is R2. Then we also have, let me call this I1, IK. Then we also have R1 as 120 ohms, right? Then the E is giving us 24 volts. So here, this resistor is not counting. This resistor is not counting, right? The R2 resistor is not counting. So R2 resistor is not counting. Okay. So the R2 resistor is not counting. Why? This is because it is parallel to what? To the IN. It's parallel to the IN. So it has been short circuited. Okay. So how can we solve this so quickly? You see, there are a lot of ways that you can use in getting your IN. But with the best way, the shortest possible way, is to find what? The source transformation of the voltage here and the resistor in series. So if I should reduce this, then we are going to have a current source which is moving what? Upward. You get it? Then you will have a resistor R1 which is 120 ohms. You get it? Yes. So something like this. So we apply a source transformation here to get a parallel resistance too. So I have my R2 which is at this end, right? And that is 280 ohms. Then you have our current source which is moving downwards, right? And this is 0.56. Then we continue with our RN. Continue with our IN. So IN is moving this way. Do you get it? Yes. So at this point, see, these two resistors, they are all parallel. Okay. So they are parallel to what? The short circuit path. So IN has been short circuited. Okay. It's short circuit. So since these two resistors, they are parallel to what? The IN path. It goes out of the circuit. They are not needed. Okay. The two resistors are not needed again. So they do not count in the circuit. So we take them off. Please, I'm pleading with you. If you've not watched the source transformation video, probably that's the reason why you might be confused over here. So watch all my videos before coming to watch this. You don't need to just jump into this. You get it? Else, if you have limited knowledge, you'll be struggling. So try as much as possible to watch the fundamental video, like watch it in series and understand the concept, because you are building on it all the time. So don't just jump into this and draw conclusion that you are confused. So watch those videos and come and watch this one before you can understand it better. So those who have watched it or those who have learned it somewhere understand what I mean by source transformation. Okay, and they also understand why these two resistors has been taken off, right? It has been taken off because it is forming a short circuit path, right? It's forming a power connection with a short circuit path. If I have a resistor here, right, and I apply a short circuit path on it, together with a load. I even proved this with a software. So watch those videos and you'll be fine. So this resistor do not count because there's a short circuit path over here. Are you okay? Yes. So these two resistors are out of the circuit. And how do we find the current source here? Let me call it IT. So with this one, it's just the voltage over the resistor. So we have 24 on 120. Are you okay? Which is equivalent to how do you call it? 120. It's equivalent to 0.2. Okay. So we have 24 on 120. 24 on 120 is going to be equivalent to 0.2. That is the current. Okay, the voltage over the resistor. So at this point, we've got a new circuit. And that circuit should be something like this. I have my current source up here, right? And I have, how do you call it? Let me change the thing. Okay. So I have another current source moving downwards. You get it? Yes. Then my IN continues over here. So my target is to find IN. So IN is at this point. That is the IN. IQ. Yes. So what will be the result for this? How can I find IN? I know that I is what? Is 0.56 and IT is, how do you call it? 0.2. You get it? So with this, the IN is basically going to be what? The bigger one, which is 0.5, I minus the smaller one, which is IT. You get it? So at the end, what do I have? I have 0.56 minus 0.2. And this one will give us 0.36 amps. So IN will basically be moving downwards. Since the bigger current is moving downwards, IN current will also move downwards. You get it? So now, we've been able to find the IN as well as the RN. So RN is here and IN is also there. So IN is 84. So RN is 84 ohms. IoT. So with this one, if I should draw a circuit, it's simply going to be something like this. I have my IN, which is moving downwards. IN is 0.36 amps, right? And I also have the resistance, which is power towards the current, RN. So I have my RN as what? I have my RN as 84 ohms. You get it? So now, let's add what we took off from the circuit. See, we took this side off. So we are going to add it to it. So this side was taken out from the circuit. Right. We are going to add it to it. So we have a current source which is moving upward and a load, right, RL. So let's draw that one attached to it. I have a current source which is moving upward, right, and a load which is termed as RL. So RL, which is 168, right? So RL is 168 ohms. Then a load, right? This is 180 times 10 exponent minus 3. So it's going to be 0.18, right? Yes. So at the end, I'm going to get my I2 as 0.18. Do you get it? 0.18 amps. Let me add the amp to it. And let me add the ohms here. Okay, now we are moving to the B part of the question. So that's the B part. The B part is saying that we should find the current that is flowing through what? The load. So the question is saying we should find IL. Okay. So this circuit can be simplified. Well, let me simplify it at this end. So we have two currents, right? One is moving upward, one is moving down. So at that point, which one is greater? The IN is greater. So I'm going to add this current together. Since one is moving upward and the other one is moving down, we subtract. Do you get it? So at this point, what do we have? We have a big current source here, which will be moving downwards because the IN is greater. So it's moving downwards. And at the end, let me call it IT, right? So IT is basically going to be, So IT is basically going to be what? 0.36 minus 0.18. Okay. And what's going to be the answer? You are going to get 0.36 minus 0.18. You are going to get 0.18 amps, right? So that's going to be the current source. Then I'll have the Rn resistor here, which is 84. So 84 ohms, right? Then I also have my RL resistor, which is 168 ohms. So we are finding the current IL. So at this point, I can apply current division. So IL is basically going to be what? The Rn all on what? Rn plus RL, right? Times the IT that we found here. So at the end, I'm going to get IL equal to what? 84 on 84 plus 168 times the 0.18 IQ. So with this one, if I should compute, I'm going to get 84 on what? 84 plus 168 times 0.18, right? And this gives 0.06 amps, which is the same as I'm moving 3 times 60 times 10 exponent minus 3 amps, right? And it's the same as 60 milliamp. So that's the final answer for the B part of the question. Okay. So please, if you are struggling to understand this, it's because probably this is the first time you are watching my video. Try to watch the subsequent videos. Okay. Watch them and understand them. And you're going to understand this one too. And also, if you have any question, just join the Telegram page. Maybe you have any question that you want me to solve for you or explain to you. Okay. Join the Telegram page and ask those questions there. So once you ask those questions, I will quickly attend to you. Some people are asking questions on that page. So if you have a question, just join the Telegram page and ask the question, and I will attend to you. And also, please subscribe to the channel. Okay, let's build a community, a nice community with my channel. So do well to subscribe and click on the notification bell icon. Okay. This is not the only video I'll be doing. In the near future, I'll be conducting several videos like applied electronics. I know applied electronics is a common course to all of you. So I'll also be conducting applied electronics also. So try to join it and let's form a very big community. So I'll see you in the next video where I'll solve extra questions on the Thevenin and Norton. I'll try to get more questions and solve under the Thevenin and Norton. IAT. So I'll solve it under the Thevenin's theorem. And that same circuit, I'll apply the Norton theorem. You get it? Norton's theorem over there. So once I'm done, we can move on to the, let's say, capacitors. That video is going to be quite short, so I'll attach capacitors to it. Then you move on. So, as it stands now, I'll ask you to enjoy the rest of your day. Okay. All the best. Bye.